First topic for this afternoon, GPS for research and accuracy issues. This is basically just a quick overview of a study we have conducted here in the city of Pocatello. And what we did is we took a bunch of GPS receivers out there and made a field test and assessed the accuracy that we could actually achieve with each of the units. So what we tested is the precision and the accuracy of a few receivers. So we compared the ProXR, which has suggested accuracy of about 50 centimeters, so it's about half a meter. The GeoXD, which is sub-meter. GeoXD using WAS, and we'll cover here more detail on WAS and issues with WAS. Then GeoExplorer 2, which has a suggested accuracy of a couple of meters, and Pharos iGPS 360, which is basically what I mentioned this morning, from an iPack and then Bluetooth connection to a GPS antenna. Pricing, GeoXD is about $5,000, including all the software. Pharos iGPS, including all the software, about $300. So there's quite the range in there as well in pricing. We'll come back to that. So what we did is we tested it for its capabilities on precision and accuracy, and we conducted a comprehensive field study which actually included 15 points throughout the greater area of the city of Pocatello. Each of these 15 points was visited 10 times over a course of about a month. And then each point that we actually collected was averaged at a 120-point average. So each point was observed 120 times, and then the average of that 120 was considered to be the true point location that we observed. And remember, those 120, for example, that averaging setting is one of the settings you can do with the GPS receiver in order to set that it collects 120 times before you record at one point. What we have also done for all the units except for the Pharos unit, which is not capable of differential correction, all the units were set to collect information that allows us to differentially correct the observations, which is basically we turn on to collect the .SSF files, and the protocol was chosen to be GPS correct. For example, for the GeoXDs. The maximum acceptable PDOP was set to 5. Here also a quick note, you can set it on all the units except for the Pharos unit. The Pharos unit, you cannot specify which PDOP you would like to observe. And remember, in the beginning we have shown that slide that sometimes the PDOP can go beyond 20 and further up. So that's a serious issue with the Pharos, that you cannot observe the PDOP. In this case, we selected a very good PDOP, but we based it on the other units. The Pharos cannot observe it, so we couldn't set it there, each location. Now, question, what is accuracy versus precision? Here, what is that? That's a bad shot, yes. That would be accurate, but not precise. Because if you take the mean of these 3 shots, you arrive right at the center. So it's accurate, but not precise. Top right, that would be not accurate, because it's off the target, but very precise, small group. The last one would be very precise and accurate. Okay, so accurate, not precise, precise, not accurate, accurate and precise. Basically, whenever we deal with precise, just imagine that this bullseye is not there at all, right? So all we are interested in is the grouping compared to themselves. We don't care about the underlying bullseye. Whenever you talk about accuracy, you're referring to some point of reference, in this case the bullseye. So the red center here, here, or here. That would be the accuracy that we want to compare it to. So for our study, what we did is the precision is based solely on the observation without consideration of any absolute point reference. So it's simply the observations amongst themselves. You could also refer to that as a relative coordinate system. That's a relative coordinate system, could be anything, any local coordinate system. The accuracy, on the other hand, is based on the comparison of the observation to the point's true location. The point's true location, in this case, however, what we did is we used a higher survey grade GPS equipment with RTK, real-time differential correction, and that is expected to be in the centimeters. That was our true point location. And that is in an absolute coordinate system, for example, WGS 84. So here we not only had our own observations, but also something else that we accepted as that is the true point location. Is the difference clear between precision and accuracy? And how we applied it to our study. Now, the results in meters at 95% confidence interval. So as we see, the first two columns are XY of the precision. The second column's XY of accuracy. Now, for example, for the ProXR, what we can see, it really meets the precision of less than half a meter. The accuracy, we can see in the Y, it's a little bit off. So it's more than half a meter. But that's still sub-meter, so ProXR performed very well. The GeoXT, precision, well in the sub-meter. Accuracy, also well in the sub-meter. Now, the GeoXT, here in front with the W, indicates that we used WAS on this unit for real-time differential correction, and then also post-processed it for post-processing differential correction. So the precision here, as we can see, is a little bit worse in the Y, a little bit better in the X, but pretty much not too much difference here. The accuracy in the Y actually went up about 20 centimeters. So the accuracy of the WAS-enabled GeoXT was actually worse than the GeoXT not using WAS. And that issue we'll revisit in a minute. The GeoExplorer, 2 meters, 3 meters, XY, precision, accuracy over 3 meters. Now the Pharos unit, precision was actually pretty good. We had a precision of about 2 meters, which is not bad for a $200 unit, compared to a few $1,000s here in the GeoXT. However, the accuracy is quite worse. So when you compare it to the true location of the point, not just to the grouping, then you actually had quite the worse observations, but still within 5 meters. And again, these numbers here are compiled from 15 points visited 10 times. So 150 observations for each of those. And then with the 95% confidence interval. So again, the Pharos, not bad. However, the accuracy That's where you see the true difference. Because why? Why do you expect this? Why is it so much worse than all the others? PDOP and differential correction. See, that's where we move the relative coordinate system, basically the precision, move it to fit that accurate point, right? In our case, that is a base station, and we use the base station in order to correct, differentially correct. If you can't make that coordinate adjustment shift from the relative to the absolute system, that's where you see then the big error here. So that's mainly due to not being capable of the differential correction. So okay? But still, you can see all the different units, pretty much what you expect and pretty much what you can see. That's also a little side note there, is all these, or most of these were actually from Trimble or Ferros. Now there are some sports devices that you can buy like at any hardware store where you see accuracy indications that are not necessarily 95% of the time. So if you don't do it 95% of the time, then these values are way lower. So that's where you see, for example, some sports devices, you can see like 10 plus minus 10 meters, right? If you would calculate it at 95% of the time, then it's actually 30 meters or something like this, if you would do that study. So here, watch out a little bit also on how to indicate the accuracy. It should be within 95% of the time. So that's what we compared it to, and they are well within the limits. So a little bit more on the results. The Ferros unit actually had no mechanism to observe the PDOP. In this case, we pretty much eliminate that deficiency by only using the Ferros unit whenever we use the other units. So on the other units, when it says it's really at the location we achieve that PDOP of 5 or better, then we turned on the Ferros unit as well. However, if you would just go out with the Ferros unit, you have no way of checking what PDOP you have at that location. So you could have a PDOP of 20, and then the results that I showed before on the table would be way worse. The next, the worst outliers observed were, for example, for the Pro XR, 0.8 meters, for the GXT, 1.2 meters. However, the Ferros was off by 8 meters on one of the point locations. The best unit is not necessarily based on one single component, but what you have to do in order to select the best unit, you have to compare the price versus the accuracy that you achieve versus the accuracy that you actually require in your study. So if you require, like you heard in remote sensing, you want to fit it in 1 pixel, 1 QuickBird pixel, where you need to be within 2.5 meter pixel, you cannot use a Ferros unit. So no matter how much you save on price, and no matter how well it actually performs in its accuracy compared to its standards, if you can't use it, it's useless to you in your study. So that's, for example, why we had to go for the GXTs in order to be able to observe the ground truthing for validation of remote sensing data. So your best unit will always be based on these 3 components. Sub-meter recommendation thus would be GXTs out of the ones that we tested. There are many others out there, but out of the ones that we tested and we have available here at the GIS Center would be the GXT. Also goes up to about 10 meters. Anything above 10 meters, the Ferros is a viable alternative, and at a fraction of the price. About 4,000 compared to 200. So it's quite the price difference there. If you have wildlife observations and you really don't care if you're within a couple of 100 yards, Faros is an excellent unit, even considering the PDOP and everything else. Any questions so far? Now, why was that WAS worse when we turned it on the GeoXT? Well, first of all, let's take a step back and actually take a look at what WAS is. So WAS is the Wide Area Augmentation System, and it consists of approximately 25 ground reference stations. And you can see here in the Stanford University screenshot here where pretty much all the locations are. So these are the ground reference stations. What to do, and then there are also 2 master stations, one on each coast. And then what they actually do is they observe the atmospheric and the ionospheric disturbances for the signal, collect that data, and send it back up to 2 geostationary satellites. So there are 2 geostationary satellites that actually transmit the WAS signal. However, it is based on the collection of those ground reference stations, those 25 ground reference stations. If you would be, for example, in Canada, somewhere way up there in Canada, would you still receive? Yeah, maybe you would still receive the WAS signal, right? Is it much use to you? No. Why not? Because there are no reference stations. So there's no way of actually observing the atmospheric and the ionospheric disturbances. And as you can imagine, the atmospheric and the ionospheric disturbances are different based on the location that you are. You know, just look up atmospheric disturbances, you know, and whatever connection you have there to the satellites, that's how your signal will be influenced. So it depends on the location. That's why we have 25 locations throughout the US. Now, for our study area over here, maybe a little bit of a zoom in here, what we see is these ones, these few stations here, are actually our closest ground reference stations. Then you have to read the text below, which says blue indicates active, gold indicates passive, and red indicates communication failure. Basically, it's out of order, right? Our closest one is where? Elko, right? Nevada. But that's out of service. So it's actually Great Falls, Montana, or Denver, where we actually get our WAS signal from. So the WAS signal, it uses the atmospheric and ionospheric disturbances that are observed at these locations that are far away from where we actually are. So that's one of the reasons. Now, there's a rule that I read up somewhere on the web page, on the Stanford's web page, and they say that, and Garmin's web page, and they say that WAS can provide up to an accuracy of about 5 meters, plus minus 5 meters. So if you have a unit that would be usually capable of plus minus 20 meters, but is WAS enabled, and you collect the WAS signal, then you can get from the 20 meters to the 5 meters. Okay? So that's an improvement. However, if we have the GeoXT, which is supposed to be sub-meter, how can WAS actually improve it if it's expected accuracy of plus minus 5 meters? Right? And it is some correction for atmospheric and ionospheric disturbances, but specifically in our location, we're so far from the nearest ground reference station that it doesn't really make that much sense, which is basically here. It also depends on the distance between where atmosphere and ionosphere were observed based to where your receiver is actually located. Make sense? So that's pretty much why we believe that wasn't all that big of a help in our study, because we don't have the ground reference station close by anywhere, and because it's expected to be 5 meters, but our unit is sub-meter, so how much more improvement do you expect versus a drift away from the sub-meter?